Alright, welcome back to Master's First Video Tutorials. In this video, we are going to, we are still journeying through the course, that is ordinary differential equation. And in fact, it's getting interesting, it's getting interesting. And where we are going is application of first order differential equation. Don't forget, you are done with first order differential equation, and that is the techniques, all the techniques starting from separable, homogeneous, exact, and all that. We also have Bernoulli and linear order and all that. Very good. Now, we are going to look at how we can relate all that we have learned in our previous video in real life, and that is application of first order differential equation. So first of all, we will be looking at application to biology, secondly application to medicine, application to economics, application to chemistry, and lastly application to physics. Alright, I will see what to do to take us through all of this. Very good. So without wasting much time, we will be starting with application to biology. And here we are going to lay emphasis on exponential decay and exponential growth. Alright, we are going to look at exponential decay and exponential growth under the application to biology. Alright, so we are starting from application to biology, and under that we are going to look at exponential decay, and after this we'll be looking at exponential growth. Very good. Please, this can relate to population and growth problem and radioactive decay. Very good. So now we have dB to be over dt. dB dt is equal to kp, or this can be written as this. Alright. Now this is the rate at which population will increase as respect to time. That is what it means. And this is the same as this. Very good. Now, anytime you have p of 0, anytime your time is 0, that means that, for instance, if t is 0, that means that you are starting at the initial. So the p of 0 is the same as the p naught, which is representing the initial. Alright, which is representing the initial population. Which is representing the initial population. Now we are saying that this k is a constant of proportionality. It's a constant of proportionality, and it should be greater than 0. That means that, there are some times that it can be negative although, but it depends on the question. If it's increased, then here will be positive. But if the population decrease, then that is going to be negative. But here we are assuming that the k is greater than 0. That means that it can never be negative. Very good. But don't conclude me. I'm also adding that it can be negative. Very good. This model exponential decay, which means the rate of decline or decay is proportional to the population or amount and nothing else. Alright, so I'm going to guide you to solve or to derive the function for b of t. That is the function of p of t itself. Don't forget that we are saying that this is the same as this, because the b dt is the same as the derivative of the population. So let's look at how we are going to, or the steps to go through to get the function back. Now you know from the beginning that integration is a reverse process of what? Differentiation. Very good. So if you have the b over dt, which is equal to kp, then we can go and find the function. Alright. So from your techniques, we can do that. We can do that. Very good. So here, when you cross multiply, you get b to be equal to kp dt. Alright. Now, for us to make this separable, don't forget, this k is constant of proportionality. The p is the population. So now we are differentiating p here. We are differentiating as respect to p here. And we are differentiating as respect to t here. What it means is that we are differentiating as respect to population here and differentiating as respect to time here. Very good. So here we can divide this p for it to be separable. For it to be separable. And here we can now move on to integrate both sides. And when you integrate both sides, then see what you're going to get. This is going to give us ln p to be equal to here, since we are integrating as respect to t, and this is a constant of proportionality, here we are going to get kt plus c. We know that after integration, we bring plus c. Very good. Alright, which is representing the family of curves. The C representing the family of curves. So here, what can we do now? We have so here we can now take the natural log on both sides. And when we take the natural log on both sides, this will cancel out. So we get P of t. I don't want to even bring the P of t for now, but that is the P of t. But it's going to be a function which is in terms of t. Alright, and this one is going to be k t multiplied by e raised to the power c. This is algebra. It's algebra. Now with this, we can let e raised to the power c. You know that e is a constant, which is 3.2 something. Alright. And c here is a constant. So the whole of this is a constant. Constant raised to the power constant is a constant. So we let this represent p naught. Alright. So after representing this by p naught, then we can say that the function is going to be p naught e raised to the power kt. Very good. So family members, that is it. That is this. That is it. So this shows the differential equation. This shows the differential equation. This shows the particular, the general solution. This shows, okay, now since we didn't leave it with the constant, now it's including with the initial. Let's say that this is a general solution. Sorry, this is a particular solution. But if we leave it like this, you know that this e raised to the power c, we can make it c. Alright. If we leave it like c e raised to the power kt, we can say that this is a general solution. But this one we have here is a particular solution. It's a particular solution. So this is a differential function, and now we have the particular solution here. Very good. Thank you. So now you can see that this should remind you of exponential decay problem. This should remind you of exponential decay problem. That is in your algebra 1 class. This should remind you of your exponential decay problem in your algebra 1 class. Very good. So let's now move on to see how we are going to use this idea to solve a real life situation. Very good. Now, let me add this. Sometimes you can be asked to write the IBP. When you are asked to write the IBP, for instance, the IBP is just the P dt, which is Okay, then the condition will come. That is P of 0 is equal to P naught. So this is going to be the IVP. What this means is that in the function of P of t, when you replace t by 0, you are going to get P naught. When you replace t by 0, you are going to get P naught. And that's exactly what we see here. If t is 0, k times 0 is 0, u raised to the power 0 is 1. When you raised to the power 0 is 1. So we get 1 here. So you're going to get here to be P naught, and the t is 0. So we now end by getting P of 0 is equal to P naught. Very good. Which is representing the initial condition. So this is how we state the IVP. There are some questions that your IVP can be true and others. Very good. So let's look at it. Alright, so let's look at our first question under the exponential decay. Alright, so on the board we have polonium minus 218 decayed exponentially. The decay rate is 23.1% per annum, per minute, and can be modeled by that is the rate of change of the population as respect to t, which is equal to negative 0.231 p. Now, as I said, it's not always that here is going to be, positive for you. Sometimes it will be negative. So if it increase, it is positive, but if it decrease, it will be negative. Very good. So looking at this, for instance, it means that it decreases. A. Find an equation that is the function in terms of t. Find an equation that satisfies the differential equation. Let P of 0 be equal to P naught. That one we know already. Very good. B. If 1,000 grams of polonium minus 218, please, is 218, is present at t is equal to 0. How much is present after 90 seconds? How much is present after 90 seconds? C. What is the half-life of polonium minus 218? So let's look at how to go about it. Because of space, I would like to clean this part. Or let me try and manage it here. Very good. So the first thing to do is to write the IVP. Alright? So the IVP is going to be dP dt, which is equal to, that is what is modeled here for us. And that is negative 0.231 P. Very good. And we have the initial condition. P of 0 is the P naught. Alright, so this is the IVP. That is all for the IVP. That is all for the IVP. So now let's quickly move straight to A. Let's quickly move straight to A, where we are going to find the equation. Where we are going to find an equation that satisfies the differential equation. Very good. So we move on. With that, we are going to only pick the differential function. Alright? Very good. So we know that dP dt is negative 0.231 p. So you know, the idea of how we solve a separable, or how we go through a separable differential equation. So here we are going to get dP to be equal to negative 0.231 p Then it's like this. You multiply, it's like you're doing cross multiplication, right? This is the same as over 1. So when you cross multiply, maybe t will come here. So for us to make this separable, then we divide the p here by this, then we get negative 0.231 p. Oh, the p is no more there. Very good. Now that we can say that it is separable, we can now integrate both sides. So when you integrate both sides, here we get ln p to be equal to, here we are going to get negative 0.231 t, then plus c, because this is the constant. This is the constant. Very good. So now we know what we are looking for. We are looking for the function of p in terms of t. So what we do here is that we take the natural logarithm of both sides. Natural logarithm of both sides. Very good. I would like to bring this part, or okay. So I can bring this part. Let me do that. Very good. So where have we reached? So now, from what we have there, they are going to get p of t to be equal to, because this will cancel out. And that's going to be e raised to 1 negative 0.2231 t. 231 t. Point e raised to 1 c. E raised to 1 c. That is it. Then here we can let e raised to 1 c to be equal to p naught. That is what was even stated in the question. So here we get p of t to be equal to p naught e raised to 1 negative 0.231 t. Very good. So that is the equation. That is the equation for the A part. That is going to be the equation for the A part. Alright, let's move on to the B. Let's move on to the B part. The B part, the question is saying that if 1,000 grams of polonium minus 218 is present at t is equal to 0, how much is present after 90 seconds? How much is present after 90 seconds? Very good. In fact, let me make it easy for you to understand. So, pardon me, I can let me do this. So the B part. Alright, so we are starting from, always we use the equation to continue it. Very good. So let's move on. So now the question is straightforward. Let me go back and read again. Where is it? The question says, if 1,000 grams of polonium minus 218 is present at t is equal to 0. So that means that if we have 1,000 grams, it was at a time when t is equal to what? 0. And we have to find how much is present after 90 seconds. So at t is equal to 0, we have 1,000. Then what is going to be at 90 seconds? What are we going to have there? Very good. So that's all what the person is saying here. Alright, so we move on with it. So now, at t of 0, that is, at when t is equal to 0, we have 1,000. We have 1,000 what? Grams. Let me add the grams. We have 1,000 grams. Then, Then, in fact, I'll make it simple for you. Then, what will be at t to be equal to 90 seconds? To be equal to 90 seconds. But please don't forget here, we are working in minutes. So we need to convert the 90 seconds to minutes, and that is going to give us 1.5 minutes. That is, when you convert 90 seconds to minutes, you are going to get 1.5 minutes. Alright. Then here we can say that we know that P of 0 is equal to 1000. This implies that P naught is equal to 1000. True or false? It's true. Very good. Because we know that P naught is equal to P of 0. So here, since this is established, then we can now go on and do our substitution. So from here we have the equation to be Okay, so we have this equation. So now let's do the substitution. So here P of t, P naught is 1000 times e raised to the power negative 0.231 t. Alright, t. Very good. So now, all that we are looking for is that at 90 seconds or at 1.5 minutes, what is going to be that? What is going to be that? Because if you are saying that at where t is equal to 0, that is at the initial stage, we have 1000. Then what is about, then what about if we are at 1.5 minutes? So the only thing that we do here is that here we put t to be equal to 1.5. So when we put t to be equal to 1.5, then that is going to be P of 1.5. P of 1.5. And that is going to be 1000 times e raised to the power. So wherever you see t, put 1.5 there. Negative 0.231 times 1.5 times 1.5. Very good. Very good. And when you point the whole of this on calculator, you end up by getting 707.16 grams. 16 grams. Please, I hope it's clear. Very good. So at the initial stage, or at where t is equal to 0, we have 1000 grams. Then what is going to be at 90 seconds? So now conclude. Therefore, at 90 seconds or at 1.5 minutes, then we are going to have 707.16 grams. Very good. So that is what that is going to be. Let's look at the C. So for the C part, let me do that here. Hope you are following, and in fact it's interesting. That's how we relate the first order differential equation in real life under exponential decay. So the C says that what is the half-life of polonium minus 218? What is the half-life of polonium minus 218? Very good. So please write. When we say half-life, what does it mean? Half-life is the length of time. Half-life, hope you are writing. Half-life is the length of time it takes for half of the substance to decay. Half of the substance to decay. Alright, so in case you couldn't write, that is the half-life. Half-life is the length of time it takes for half of the substance to decay. So this is a general explanation of half-life. So here, what are we talking about here? What is the half-life of the polonium minus 218? So we are looking for the time or the length of time it takes for half of the substance. So the substance here will represent the polonium minus 218 to decay. So let's do that. Very good. It's not difficult. Now we pick it from here. P of t is equal to P naught e raised to the power. Don't forget we are looking for the time. So 2, 3, 1, 2, 3, 1, or 2, 1, 3, 2, 3, 1, 2. Very good. Very good. Alright. So that's that. Now I'm coming. Alright, so from here we move on. Now we know that at the initial stage, where we have that is 1000, at 1000, at where t is equal to 0, we have p of t, or let me say p of 0 to be equal to 1000. Alright, very good. So here, by substitution, that means that if you are looking for the half-life, you take half of the 1000, half of the 1000, and that's going to give you 500. Please hope you can see where the 500 is coming from. So half of that is going to give you 500. Alright, I will also show you another method to get the half-life easy. So this is going to give you 500. That is half of the 1000. Now the P naught here is 1. Alright, the video paused while I was talking, explaining this. Alright, so that is that. Here we reach the right. Very good. So now we are saying that the 500 is coming from taking half of the P naught. Very good. And that is what you're going to get for that. So here you divide both sides by 1000 and you end up by getting this. And with this, you divide this one, cancel this to get this. So the half-life means that we are looking for t. So for us to get t, we divide by this and we end up by getting this. This is the approximating value, alright? This is the approximating value. That's why you can see this sign. This sign is different from equal to sign. So this will be approximating to 3 minutes. This will be approximating to 3 minutes. Alright, very good. Please, another way to get the half-life. This is a shortcut. This is a shortcut to get the half-life. That is going to be t is equal to ln half, because always this place will give you half because you are taking half of the P naught. So always this will give you half. So it's going to be half of the ln over k, which is the constant of proportionality, and that is that. And that is that. So here you can see that from the question, the constant is negative 0.231. And that is where you are going to end. So this is another short method of getting the half-life. Thank you. Think we are now with the exponential decay. There are a lot of questions, and I would like you to go and look for some and solve it. Very good. Let's move on to exponential. That is going to be exponential growth. Exponential growth. Alright, and trust me, you're going to love it. It's similar to what we have just done. Don't forget, all this we are doing is under application to biology. Under application to biology. Alright. So the exponential growth is the same as population and growth family. Then see you there. Alright, so here we look at our second question under exponential decay. Uh, so 2. A certain radioactive material decay decays at a rate proportional to the amount present. At a rate proportional to the amount present. At time t is equal to 0, there are 50 milligrams. At time t is equal to 0, there are 50 milligrams. After 2 years, 20% has decayed. 20% has decayed. A. Find an equation to model this decay. Wow. B. How much is left after 5 years? C. What is the half-life of this material of this material? And here that is representing the substance. How we are getting it? Very good. So what is the half-life of this material? So let's start. Solution. So we go for the IBP first. Okay, that's the first thing to go for. In fact, there are some questions that you can ask. A. State the IBP or write the IBP. So what is going to be the IBP then? What is going to be the IBP then? Very good. So here, a certain radioactive material decay at a rate proportional to the amount present, and that is going to be the P dt, which is equal to Kp. Here is going to be positive but not negative. Kp. Alright. Now, at time t is equal to 0. Yeah, you know when that is going to be P not is equal to 1000, like the one that is so low. So always take your time when you are solving it. At time t is equal to 0, there are 50 milligrams. So at P of 0, then we have 50 milligrams. 50 milligrams. Alright. After 2 years, 20% has decayed. After 2 years, 20% has decayed. That means that 80% is not what? Decayed. Alright, so this implies that after 2 years, that's what we are supposed to. After 2 years, now the initial, that is the P naught, is 50. Alright, but after 2 years, 20% decayed. That means that 80% is not decayed. So what we do is that we multiply this 50 by 80%. By 80%, which is the same as 50 times 0.8, and that is going to give you 40 milligrams. Love this question. 40 milligrams. I hope you can see how it is going. Interesting. Think like that. Very good. So now let's go and find an equation to model this decay. So that's going to be the IBP. Alright. A. So let's go for the A. And we know that this, when you solve the differential equation, in fact, that is even the first thing that we did. The differential equation, when you solve it, you're going to get P of t. So you have no need to go and solve again. Just quote and go your way. P naught e raised to the power kt, where k is greater than 0. Alright, so let's move on. So now, yeah, don't forget that we had P at square time after 2 years, we have 40 milligrams. So the P of T, here is going to give us 40. Then the P naught, what is going to be the P naught? The P naught is 50. The P naught is 50. The P naught is 50. Alright. Then here is times e raised to the power kt. E raised to the power kt. But what is t here? What is t here? Alright, tell me what is t here. So you can see that the t here is 2. Because, sorry. Oh yeah, the t here is 2. So we are looking for the constant of what? Proportionality rather. Before we come back to write the equation. Alright, so for you to get the equation, you need to get a constant of proportionality. In the previous example, or in the example 1, the constant of proportionality was given to us already. So, but here, we don't know the constant of proportionality. So we need to go for the constant of proportionality. This is just P naught, that is at where T is equal to 0. There are 50 milligrams. So at P naught, we have 50 milligrams. But the question continues to say that after 2 years, 20% has decayed. That means that 80% did not decay. So you multiply that by this, and you are going to get that for that. Very good. So that represents the P of T. And before you can get this K, you need to get P naught, P of T, and T. So here we know that T will be after 2 years. So 2T. Sorry. 2K, because we are looking for K, right? Very good. Then we can divide both sides by 50. This is going to give us, you know, when you divide both sides by 50, 50 will cancel out. Let's bring it. Let's cancel this. This is going to give us 0.8 equal to e raised to the power 2k. Alright. So for you to get k, what will you do? You take mean of both sides. Ln 0.8. Ln e raised to the power 2k. Okay. So now, here, this will cancel out. Let's continue here. So with this, you are going to get 0.8 is equal to 2k. That is equal to 2k. So what will you do to get k? Divide both sides by 2. So you get k to be equal to ln 0.8 over 2. And this is going to give you the constant of proportionality, and that's going to be negative 0.11157. So you can see that here, you cannot say that k will be greater than 0. So let's leave the condition. Let's leave the condition here, because we have realized that now we are getting k to be negative. Very good. So that is how we do to get the A. So for you to write the equation, so the A. Now, after getting the constant of proportionality, that doesn't mean that you have ended with the question. You have to write an equation. So here, you now come back and write the equation. So P of T is going to be equal to P naught e raised to the power kt. So here the P of T will be equal to P naught is 50. E raised to the power k. K is negative 0.11157t. So this is the equation for the differential equation. So now that's going to be the the particular solution. So this is the particular solution for the question. So we are done with the A. Hope it's interesting. Here, you don't know the K, so you can't go for the equation. You need to go for the K. Very good. B. How much is left after 5 years? Oh, it's still not difficult. How much is left after 5 years? Let's go for that. How much is left after 5 years? B. So this is 2B. How much is left after 5 years? That is at where t is equal to 5. What is going to be that? So just call this. P of t is equal to 50 e raised to the power negative 0.1157t. So you can see that we are using this to get it. So if your k is wrong, everything is going to be wrong. In fact, I mean the constant of proportionality. If you get it wrong, everything is going to be wrong. So now here, t is equal to 5. So what is going to be that? 50 times e raised to the power negative 0.11157, and t here is 5. Alright. When you put your calculator, you're going to get 28.6 milligram. 28.6 milligram. Alright, let's go for the C. Oh, that is very, very easy. That's going to be easy for us. In fact, we are going to use the short method. The C says that we have to go and find the half life. We have to go and find the half life. And we know what a half-life means. Half-life is the length of time it takes for half of a substance to decay. So we are looking for the length of time it takes for half of the material to decay. And that is going to be half-life is T is equal to ln half over, this is a short method, okay, over K. So that's going to be ln half over, what is K? The K is negative 0.1157. And when you do that, you are going to get it to be approximated to 6.2 years. 6.2 years. Beautiful. In fact, you can use the long method, you still get it. Okay, you still get it. Still the same thing, choose the one that you go by. So this ends the exponential decay. Let's look at exponential growth. We will be looking at exponential growth in our next video, and that is the same as population and growth problem. Population and growth problem. How death rate affects the growth of the population. Very good. See you there.